In 1934, a physicist at Cambridge University calculated something disturbing. He took everything known about bird flight at the time: wing size, body weight, air resistance, energy requirements, and he applied those calculations to the hummingbird. The math came back wrong, not slightly wrong, completely wrong. According to every principle of aerodynamics that existed at the time, the hummingbird could not fly. Its wings were too small. Its body was too heavy for those wings. The energy required to move those wings fast enough to generate lift exceeded what any biological creature could possibly produce. The hummingbird was aerodynamically impossible. The physicist published his findings. Scientists debated. Nobody could find the error in the math, and the hummingbird didn't care. It kept flying. It kept flying backwards and sideways and hovering in place for minutes at a time, doing things that no other bird on Earth can do, doing things that the laws of physics said it couldn't do. For 90 years after that calculation, scientists argued about how this was possible, and what they eventually discovered was not just an explanation for the hummingbird, it was a discovery that changed aerospace engineering, changed our understanding of energy itself, and revealed that this tiny bird, weighing less than a penny, operates on biological principles so advanced that we are only now beginning to fully understand them. Today, we are going inside the impossible biology of the hummingbird, the heart that should explode, the wings that shouldn't work, the brain that processes the world faster than any other vertebrate on Earth, and the survival strategy so extreme that every single night, this bird does something that would kill almost any other creature alive. By the end of this video, you will never look at something small and dismiss it again. Let us start with the wings, because this is where the impossibility begins. A hummingbird beats its wings between 50 and 80 times per second, every second. Not during bursts of speed, not during takeoff. Every single second it is in the air. 50 to 80 complete wing strokes per second, every second. The energy required to do this is extraordinary. A hummingbird has the highest metabolism of any warm-blooded animal on Earth. Its heart beats up to 1,200 times per minute at peak activity. For comparison, a human heart beats around 60 to 100 times per minute at rest. A hummingbird's heart beats 12 times faster, while the bird is doing the aerodynamic equivalent of holding a helicopter hover. But here is the detail that took scientists decades to understand. The hummingbird does not fly like other birds. Other birds generate lift only on the downstroke. The wing pushes down, air is displaced, the bird rises. The upstroke is mostly a recovery stroke, repositioning the wing for the next downstroke. The hummingbird generates lift on both strokes, down and up. Every stroke in both directions produces lift. This is physically different from every other bird that has ever been studied, and it is the reason the 1934 aerodynamic calculations were wrong. The physicists calculated hummingbird flight using the same model as all other birds, one direction of lift. But the hummingbird uses two. When researchers finally measured this in detail using high-speed cameras and airflow sensors, they discovered something that immediately went to aerospace engineers, because this same principle, generating thrust in both directions of a stroke cycle, is exactly what helicopter designers had been trying to achieve for decades. The hummingbird had already solved it, millions of years before the first helicopter flew. But the wings are only the beginning of the hummingbird's impossible biology, because to power those wings, this bird needs energy at a rate that should be biologically catastrophic. A hummingbird consumes nectar almost constantly during daylight hours. It visits between 1,000 and 2,000 flowers every single day, not because it is greedy, because it has to. The energy demands of that wing speed are so extreme that if a hummingbird stopped feeding for more than a few hours during the day, it would die, simply run out of fuel, and starve. Its metabolism is so fast that it processes sugar into usable energy faster than almost any other biological system studied. Scientists measuring hummingbird metabolism found that these birds can convert sugar to flight energy with an efficiency that outperforms most aircraft fuel systems. Gram for gram, calorie for calorie. A hummingbird extracts more usable energy from its fuel than a jet engine extracts from aviation fuel. That statement sounds impossible, but it has been measured repeatedly, and there is more. A hummingbird's heart is proportionally the largest of any bird relative to body size. It makes up around 2.5% of the bird's total body weight. In humans, the heart is around 0.5% of body weight. A hummingbird's heart is 5 times more proportionally massive because it needs to be, pumping blood at 1,200 beats per minute to fuel muscles that never stop, operating at a sustained intensity that would destroy any other cardiac system within minutes, and yet the hummingbird's heart lasts for years, sometimes more than a decade. Scientists studying hummingbird cardiac tissue discovered structural adaptations that prevent the kind of damage that kills human hearts under extreme stress. Adaptations that cardiac researchers are now studying to understand heart disease. Because once again, this tiny impossible bird has already solved a problem humans are still trying to crack. But here's the part of the hummingbird story that most people never hear. The part that makes everything we just discussed even more extraordinary. Every single night, the hummingbird dies. Not literally, but almost. The same metabolism that requires constant feeding during the day becomes a lethal problem at night, when there are no flowers to feed from, when there's no light to fly in. A hummingbird burning energy at its normal daytime rate through the night would consume all of its fat reserves within hours and die before morning, every single night. This is not a theoretical problem. This is the mathematical reality of the hummingbird's energy system. Daytime metabolism plus no food equals death every night, unless the hummingbird does something extraordinary, and it does. Every night, as the temperature drops, the hummingbird enters a state called torpor. Its heart rate drops from 1,200 beats per minute to as low as 50 beats per minute. Its body temperature drops from around 40 degrees Celsius to as low as 18 degrees. Its breathing slows to almost nothing. It becomes cold to the touch. It does not respond to sound or movement. To any outside observer, it is dead. Scientists who first documented this behavior described picking up torpid hummingbirds and being certain they were holding a dead bird, until the sun came up, and the bird woke and flew away. The hummingbird doesn't just survive the night. It essentially pauses itself, drops to the lowest possible biological function that still maintains life, saves every calorie it has, and reboots in the morning, every single day. This process is so precise, so biologically controlled, that researchers studying torpor in hummingbirds have called it the most dramatic nightly physiological transformation documented in any warm-blooded vertebrate. Now we need to talk about the hummingbird's brain, because everything we have discussed so far requires something extraordinary to coordinate it. A biological computer powerful enough to manage wing beats of 80 times per second, to process visual information fast enough to navigate at full speed, to calculate nectar availability across territories of hundreds of flowers, to time the daily torpor cycle with precision, and to do all of this simultaneously. The hummingbird has the largest brain relative to body size of any bird species, proportionally larger than an eagle, larger than a crow, larger than any bird known for intelligence. But it is not just the size that surprises researchers. It is what the brain does. Hummingbirds can remember every flower in their territory, not approximately, precisely. They remember which flowers they visited today, which ones have refilled with nectar, which ones are empty, which ones belong to rivals. Researchers testing hummingbird spatial memory found that these birds maintain a mental map of their territory with an accuracy that rival GPS systems struggle to match. And here's the part that genuinely astonished scientists. Hummingbirds time their flower visits, not randomly, but according to the refill rate of each specific flower species. Different flowers refill at different rates. Some take 20 minutes, some take an hour, some take several hours. The hummingbird knows this. It visits each flower at approximately the correct interval to find it refilled. Not all the time, but far more often than random chance could explain. Scientists call this episodic-like memory, the ability to remember not just what happened, but when it happened, and to use that timing information to predict the future. This type of memory was once considered exclusive to humans and a few primates. The hummingbird has it too. If this tiny bird is completely changing the way you think right now, hit like so more people can discover this incredible story. Now here is where the hummingbird story stops being just biology and becomes something that touches almost every part of modern technology. The dual-stroke lift principle discovered in hummingbird wings directly influenced the design of micro-aerial vehicles, small drones built for surveillance, search and rescue, and environmental monitoring. Engineers spent decades trying to build drones that could hover efficiently in tight spaces. The hummingbird had already solved the problem. Its wing mechanics are now directly copied in drone designs used by military and research organizations worldwide. The hummingbird's energy conversion efficiency has influenced research into biofuel processing. The way its muscles extract maximum energy from sugar is being studied as a model for more efficient fuel cells and energy storage systems. The hummingbird's cardiac adaptations are being researched in the context of human heart disease. Understanding how a heart can sustain 1,200 beats per minute for years without the damage that would kill a human heart in minutes could lead to treatments for cardiac stress conditions. And the hummingbird's torpor mechanism, the nightly shutdown and revival, is being studied in the context of long-distance space travel, because the same challenge a hummingbird faces every night, keeping a biological system alive with minimal energy over long periods, is exactly the challenge engineers face when designing life support for multi-year space missions. One small bird, weighing less than a penny, quietly providing solutions to some of the most complex problems in modern engineering, medicine, and space exploration, while visiting 2,000 flowers every day, less than 3 grams, a wingspan smaller than your thumb, a heart beating 12 times faster than yours, wings moving 80 times per second, a brain that maps its world with GPS precision, a nightly death and resurrection so controlled that scientists still call it one of the most remarkable physiological processes ever documented, and a set of solutions to problems in aerodynamics, energy, medicine, and space travel that human engineering is still working to fully understand. The hummingbird should not exist. The 1934 physicist was right about that. By the rules of physics as they were understood then, it cannot fly, but nobody told the hummingbird, and so it kept flying. Backwards, sideways, upside down, hovering in the exact spot where the math said it was impossible to hover, every day for 50 million years. Perhaps that is the most important thing this impossible bird has to teach us. Not the aerodynamics, not the cardiac biology, not the memory system, but this. The rules were wrong. They were written without knowing what was possible, and the hummingbird simply never read them. If this story changed the way you see what is possible, subscribe to Birdhearts so you never miss another incredible bird superpower story. And tell me in the comments, which is more impressive, the hummingbird's wings, its heart or its brain? I'll see you in the next one.